Emma, maybe you can start by introducing yourself a little bit more since you're last in the group,
Sure.
and then we'll turn the presentation over to you.
Excellent. So Emma Raymont, I work for McGran. I just hit 20 years at McGran, actually, which is a really long time to be anywhere. And I am the director of engineering. I've done all sorts of things over my career at McGran. It doesn't feel like one job. At the moment, I do a lot of work both in retrofit, energy efficiency retrofits in multifamily housing, and also working on our high performance MEP design side, which is sort of more why I'm here today. Yeah, I'm a licensed professional engineer. I have licenses in Connecticut, Pennsylvania, all sorts of places up and down the Eastern Seaboard. And McGran has done a lot of work. I mean, in Connecticut, our operations does mostly verification work like Nicole does. But our team out of New Jersey has done MEP design work for many years. And so we're excited to be, maybe doing more of that in Connecticut. And I'm hoping to get up to Connecticut a little bit and meet with Susan's team on the project. We're starting off with them. So this is a good opportunity to start meeting some of the folks up there and, talking to everybody about how we do great things in housing. So I just wanted quickly, and we can, so the presentation that was AIA approved that I started from for this presentation is called Designing Net Zero Energy Housing. So it's not specifically branded as Passive House, but a lot of it is very similar scope. And Nicole and others here have some Passive House experience, and we can sort of comment as we go. I'm happy to sort of make this more of a dialogue. And hit those things that are of interest to people. So, all right. So as I said, the sort of AIA presentation we have approved is sort of designing for net zero. So that's where we're going to start. But, a lot of it is relevant all across the board. We're going to talk a little bit about, what does net zero energy actually mean? How do we get there? What are the design strategies we've used that have been effective? And then touch on the value proposition at the end. And again, as I said, happy to keep this as a dialogue. There's a lot of knowledgeable people here to sort of add to what I have to say. Mandatory AIA objectives for those of you who care. What is net zero? How can we get there? What's the value? And so consider that done. So defining net zero. So actually not an equation like this, right? This is a long, complicated equation for which I don't know what it solves for. Actually, net zero is pretty easy, right? In theory, it's pretty easy. Let's make at least as much as we spend energy-wise, and that's the sort of fairly simple definition. It's not complicated inherently. That said, so what does that mean? It means we have our building HVAC spend, water heating spend. What are we using for plug loads? What are we using for lighting? All of that energy use, whatever it might be. We want to generate more either on-site solar, community solar, some sort of renewable carbon credit. So here's where we start to think about what does that actually mean? Do we need to do all of that on site? Do we have other options for it? And that's when the debate starts. So while inherently fairly simple, in practice, depending on who you're talking to and what program you might be trying to appeal to, it's a little bit different. Just sort of to put that in words for those people who like a nice definition, it's always good to have a definition to start with. So a zero energy building combines energy efficiency, renewable energy generation to consume only as much energy as can be produced on site, or perhaps in some other way to offset over a specific time period. So that's a nice definition to start from. In terms of how we get there, we're going to get into that. but there are, and FIAS, the passive house certification, as well as various, getting to net zero. There's Energy Star designed to net zero. There are a lot of tools out there to help us get there. And even some of our more standard tools like Energy Star and LEED have inherently built into them all of the things we need to get there. So it's not magic, right? And it's not that as complicated as you would think. It basically means doing a lot of the best practices that all of you and those of us in the industry have been working on and working with for some time. So keeping on. The things that start to get complicated in terms of what is net zero energy is, when we start to get into the weeds. So when we say the energy that we're generating, the energy we're using on site, do we mean the actual, kilowatt hours from that site? Or are we talking about what it actually takes to generate those kilowatt hours somewhere else at that power plant where we might be getting that energy from? So that's site versus source energy. Do we want to talk about carbon? A lot of people like to talk carbon as opposed to, BTUs. Which way are we looking at that? And if we are talking carbon, are we talking just that operational carbon? Like, what does it take to run the building? Or are we also talking how much, energy / carbon did it cost to make the bricks, right? I just read a whole article about how brick production is actually fairly intensive from an energy perspective. So are we going to try to offset all of it, what it took to make all of the materials that we're putting into our building? Or are we just talking operationally? And then, are we talking about our energy model and what our energy model says? We're going to design to hit this target that we've modeled and we think is a pretty good estimation, but it's an estimate, right? It's an educated and, smart estimate, but it's not what's actually going to happen once we start running the building. That's always going to be different. So are we talking about design for net zero? Or are we talking about actually trying to achieve that in the building when we're running? And then, Nicole and I, and maybe some of the rest of you, were at FIASCon a few weeks ago. And, most of the builders that we work with and the projects we work on, when they're achieving net zero, are going all electric, right? You can offset electric with solar easier. But some people are still, there are projects where, and locations where, sometimes you are still tied to gas, or for whatever reason, that's part of your project. Can you do that and be net zero, right? Some people say, absolutely not. Once you use your gas, it's gone. There's no way to offset that, right? It's not a renewable. And some people say, oh, no, there's a calculus here that I can offset with carbon credits or whatever other offset strategy that you have. So, inherently, generate at least as much as you're using, but there's a lot of different ways you can define what you're using. So the process to get there, and I think for our purposes as sort of design professionals, talking more, my role as an engineer, I am more focused on that operational use, right? What can we do in our design of the building in terms of, and let me just go to the next slide here, in terms of reducing the wasted energy from a poor building design in terms of insulation, et cetera, air sealing, all of those things. How can we reduce our load? And then how can we design systems that are very effective at meeting that load in an efficient way? And then, then you get to your renewables. There's some interplay here, right? How are we going to, and I think the next slide does some of this. So, on a site, right? there's only so many ways each site can have a building located on it, right? So, it may even start with site selection, right? If you're going for a net zero energy building, you want to pick a site where you have the opportunity to potentially rotate that building so that you're taking best advantage of winter solar gains, but allowing yourself to put in shading so you don't overload your cooling load in the summer. Are there shading? Are there other buildings that restrict you? Are there trees you can preserve to, depending on, high rise, low rise, whatever your building type. How can you manipulate from an architectural standpoint the shape of that building, so that we maximize our internal volume to external surface area, right? So we minimize the amount of surfaces through which we're losing and gaining energy. And again, overhangs, slopes, all of those kinds of things. And, and then window to wall range, it's going to be really hard to get to net zero in, an office building or a building with an awful lot of glazing, right? Typically, when we do net zero buildings, we want to bring down our glazing percentage. Not that there aren't ways to do that. And if you want to put an awful lot of solar on a building, there's an awful lot you can do. And just generally, envelope decisions, right? Making sure that we choose good materials for our envelopes and do our air sealing details well. System choices, again, talking about fuels, different types of equipment that we want to specify. And finally, we come to our end users, right? Who's going to be in this building? And thinking about, is this a senior building where we may want to plan for higher indoor temperatures than we might otherwise, right? Our energy models usually call for a 68-degree indoor design temperature. In a senior building, usually it's at least 70, and sometimes more than that, just to keep people comfortable. And we see a lot of retrofit in existing senior buildings, and doesn't work to keep the temperature at 68. So we want to keep that in mind. And conversely, if you're looking at a building for a lot of young families, your domestic hot water load is going to be higher than it will be in your senior building. So we need to not assume that, we want to make good assumptions about how much we're actually going to be spending in our domestic hot water usage based on our population, because otherwise we could overshoot our target. All right. So these are sort of, I didn't make these graphs, but they are actually, if you start to look at them, they make a lot of sense. So if you look at the one on the left, the purple dashed lines showing the sort of little chart there is sort of when does the effort happen in a project? So typical design projects, you do a small schematic phase, a little bit of design development to sort of quantify that and clarify that. And then most of your work is at the CD phase, right? Your construction documentation phase. What we want to do on projects like this is shift that effort earlier in the process. And the sort of swoop purple line there is showing you how, it's fairly logical, right? The earlier we make choices, the easier and more cost-effective it is to do that, right? If we decide, in CDs that we want to hit net zero and we've got a building which hasn't considered this early on, we're going to have to redesign a whole lot of stuff in order to get there. So we want to take our design team, get them engaged early, and start looking at those things that are key factors in achieving that goal. And the sooner we do that, the more cost effective it is to impact, to get to where we're trying to go. And the converse one is the red swoop in the other direction, right? It costs more the later on we have to make a design decision. And I'm sure we've all got stories about, field changes and how much that costs. So the sooner we can do that, make good decisions, the better. The other chart on the other side is a little bit about sort of thinking on holistically on the life cycle costs of buildings, right? So it costs a lot to build buildings, and finding the appropriate funding and support and resources to build a building is challenging enough in the first place. There's a lot of studies now that if you do it right, building a passive house net zero energy building isn't necessarily a whole lot more expensive. That said, there are some choices we want to make at the beginning. We want to buy better windows. We want to put in exterior, more rigid insulation. We want to buy the best efficient equipment we can, because that upfront cost over the life cycle of the building is less than your operational costs, right? Which is why, it's the most successful projects we see in net zero passive house type high performance buildings are built by teams that are going to be engaged with the building through the life cycle, right? Somebody who's going to own it and manage it, and be engaged in it. Because if you're just going to flip it, you're going to be prioritizing that much lower first cost, because you don't care what's going to happen when you're gone. So having the people who are going to be owning this building and running this building engaged as stakeholders, so that we can prioritize some of those upfront costs to make the back end better, is sort of the point of that graph. All right, so just to touch again on one of the key things that we need when we're doing aiming for net zero or for passive house, is that we need energy models. So the typical process, if you're doing an energy model, is to end up doing that sort of maybe at the end of design development. You do a model and then you finish it during CDs, and then maybe you do an as-built model. Sometimes the model is only for code compliance. If you're doing Energy Star, you might do something like this if you've got a fair degree of confidence that you are going to hit your goals. But in these very high performance net zero energy buildings, you need to think differently. You need to be doing some modeling right at the very beginning to make those important early decisions about how you're going to rotate the building, what the massing is going to look like, where you're going to put windows, if you're going to, the orientation of your windows on your building makes a huge difference. And so being able to model that early on. So an upfront sort of basis of design model, sometimes called a box model, it's not intended to be a detailed model with all of the pieces and you're going to end up with at the end, but it's enough to look at massing. And in fact, as an industry, we're catching up with this. Like in Revit, an AutoCAD's 3D modeling tool, you can actually do this if you're so inclined as an architect. There are tools in there that can help you do some early modeling without, complicated modeling software to start making these decisions intentionally upfront. And then you want to start to iterate. And at some point in there, if you haven't engaged a team to do your energy modeling upfront, and if you're doing FIAS, you want to do that. If you're doing a FIAS, passive house model, you want to start that model early and not, use that tool, because that tool has very specific inputs and you want to engage your passive house consultant at a very early point in the design. And then you move into like you did with the other, we move into a design development, and then, depending on whether we're going for net zero operationally, you end up, maybe updating your model later on to sort of match what actually happened in your building. So tools that are available. So if you're looking at passive house, you are tied to the WUFI model. WUFI is WUFI. If anybody, I don't even remember what it stands for anymore. It's a tool. Passive house is a standard that came out of Germany. The tools are still attached to some of the people that started the initial program. FIAS, passive house in the US, I think they're trying to get away from the long name and they're just using the FIAS moniker now. Has its own tools as well, but they're tied to the old ones. It's a great tool in a lot of ways. It's very robust. models more than energy, right? It models one of the things that's really critical in very tight buildings, like what we do for Passive House, which is hygrothermic, so moisture. Like, how does moisture move through our envelopes, which is one of the really critical items, and where as an industry we've fallen down in the past, right? We start to tighten things up and don't think about where the condensing surfaces are going to be in the building, and then we end up with moisture issues in buildings. So WFI is very helpful in that way because it analyzes that as well. It does have something of a reputation for being potentially overly optimistic in its energy use. It's getting better, and you can make some different assumptions in there and use it as a good estimating tool. But you need to be working with somebody who understands the tool well and can help you use it appropriately to get to good estimates for actual usage. ASHRAE modeling is, 90.1 ASHRAE energy models are sort of the, bread and butter of the industry. In some ways, it's a large building energy model. It can be compared to whatever baseline building you're looking at. It's frequently used for code compliance and also for LEED, Energy Star, and other tools, other programs. Can be a little bit more costly. And the last option is to do individual unit level modeling. And so depending on the scale of your building, if you're doing townhouses or stacked flats or something smaller, the ERI energy level, unit level modeling is potentially sufficient for you. And in fact, on some of the projects that we worked on, we do multiple kinds of energy modeling. We'll do some individual unit modeling to understand how that's going to look, as well as the whole building model. And sometimes we'll do the unit modeling first because it's easier and cheaper, and we can get that done pretty quickly to get a sense of where things are going to land. And then we may go into the bigger model later. So lots of good tools out there. And very useful and necessary if you're heading for net zero or for Passive House. All right, but into the really fun and interesting part of it is what do we actually find that we do in these buildings that has been successful for us? So it comes down to sort of what we've been on the McGran team calling the 3 E's. So envelope, equipment, and engagement. So envelope, we all understand. Equipment is fairly standard too, right? All our HVAC stuff. And engagement is, and Nicole did a presentation at FIAS about this, like what happens when the people actually get in the building and don't understand it, don't know what's supposed to be happening, and don't know how to operate their equipment. So we need to make sure that we have a fairly significant education component. And most of these above code programs are require you to put together a operator manual. But is that something that you're actually going to hand to Joe Senior living in this apartment to educate them on what's going on with the building? Probably not. So not to mention, aside from user behavior, once systems start to operate, and I feel really fortunate to have done a lot of retrofit work because we start to see what actually happens in buildings over time, right? Ventilation systems get turned off because they didn't work or they were loud, or the building guy didn't, was not the first guy who was there or woman, and just turned it off and didn't realize what impact that would have. All of the temperature settings got turned way up because somebody complained and nobody ever noticed. So paying attention to what happens after the occupancy happens and working on that is a critical piece of it. I'm going to start with the equipment side. It's my area of expertise, and I could talk about it for hours. So I'm going to do a fair. So when we start talking about equipment, a lot of people say, okay, what's the HVAC going to be? So I wanted to just, I often start when we talk about high performance buildings, breaking HVAC into pieces, right? Best practice in high performance buildings is to separate these things out. So we want to talk about our H and our AC, like our heating and our air conditioning, our heating and our cooling. That's one piece of it. And the other piece is ventilation. And especially in passive house buildings, ventilation is absolutely critical. We're fortunate at this point that the codes have sort of caught up with us, right? And almost all buildings we're building now are tight enough that ventilation is mandatory, some sort of mechanical ventilation. And the other thing is, you know, over the last 2 years, I have had more people be interested in ventilation than I have had in the rest of my 20-year career, right? Ventilation has become front and center as part of the, you know, our response to the pandemic. So understanding how to do ventilation effectively so that it doesn't get turned off, so that it achieves the level of appropriate indoor air quality so that people can feel safe in where they're living and in the common areas that they're building, is something that we're really being challenged to pay attention to. And in passive house buildings and LEED buildings and Energy Star buildings, where we've been talking about this for years, we're ahead of the game. I will say there are some things that are allowed under some standards that we don't recommend in passive house buildings and recommend less after the, you know, in this sort of pandemic era. We really are focusing on balanced ventilation, and the image here is for an energy recovery ventilator, and I'll talk a little bit more about that. The last thing to say here before I move in to talk about some of these systems more specifically is talking about latent loads. So while it's inherently part of your sort of air conditioning typically, so latent loads, I mean moisture and humidity. So I live in the, you know, I live in Pennsylvania, which is a lot more like Florida than it used to be. And you guys in Connecticut are, you know, in the same boat, right? The number of contiguous days of high humidity, hot temperatures has dramatically increased just over my, you know, 10, 20 years living and working in New Jersey. You know, the last 5 years, we've had much longer periods of hot, humid weather than we ever had before. And what that means is that, and it's not only that, it's also that we have lots of shoulder season times of fairly humid days with maybe not super high temperatures, right? Which means usually the way we manage moisture is to run our air conditioning system, and air conditioning systems inherently dehumidify. You run your hot, humid air across a cold, cooling coil, the moisture condenses, get rid of your humidity. When we're talking about really low load buildings, we're not running that unit enough because our loads are so low. We've hit temperature a long time ago, but we could still have moisture in the space, which makes it not as comfortable. And you need to handle it for both comfort and for durability reasons. So I'll touch on that a little bit later. But that's just to break up what we're talking about in terms of equipment. The other thing not in this sort of HVAC scope is hot water, but we'll talk about that as well. So staying with the heating and cooling side, the system type that we see most frequently in our high performance buildings is some sort of inverter driven heat pump technology. So this is a plan layout for a ducted ceiling recessed heat pump, and you can see on the left what that looks like actually up in a ceiling. This is not a picture of the unit that you're seeing in the drawing. That one hasn't been built yet, but it's the same idea. They tend to be fairly wide, fairly narrow, with ducting off each end, as you can see here. And the way we usually install them in multifamily is that they are dropped below the rated assembly. Which has some inherent challenges, right? You need to, for your fire rating, and I don't know that the one on the left is showing the details that happen with fire rating, but typically in multifamily, you're gonna have to build your fire rated ceiling, and like you would with any kind of soffitted ductwork or equipment, drop that unit down. You don't have to use this kind of unit. People do because of the space saving nature. You don't take up a closet. You can also buy them to stick in closets, and that works too. A little bit easier for maintenance in a closet, but, a little bit less rentable square footage, right? You lose closet. So on the drawing here, you can see we dropped the bathroom, the closets, and the laundry area, and basically ran all the ducts there. The advantage is we stay below the assembly. We don't have any fire dampers, which is a cost savings. And because we've built this really tight envelope, right, and we've addressed air leakage, we're not feeling the need to run our ductwork to the perimeter, right? We've got a good piece of equipment that can achieve an appropriate air distribution so that we can get that air out across the room and get a nice airflow mix and distribution. And we're not having to compensate for leaky cold windows and walls because we were addressing that in other ways. So that's one of the real advantages of this. And this is where like some of those cost savings occur, right? If we don't have to run ducts so far and we can make our systems really small, although we need to really be paying attention to details and maybe buying slightly more expensive equipment and more insulation, at the same time, we're keeping our mechanical systems really small, right? And we're not having to run them all the way to the exterior. And so, there are some balancing offset items here when we start to build really good buildings. On the right, the picture is not very good quality, but what we're doing with the building in the middle there where the plan comes from is we're actually going to locate these units on balconies. This particular architect has some fancy detail for a screen in front of it, so they won't actually be sitting quite so visually obviously on the balconies. That said, I'm in the middle of another project where we're retrofitting this solution, and they're going to be just like that. And the owner is delighted to have them there because they're getting rid of a very inefficient, large, old, leaky hot water distribution system throughout the building and putting all of that heating and cooling burden or cost onto the tenant meter, right? So it's not going to be centrally metered. It's going to be all individually metered. So as I said before, there are a lot of different types. This is not showing a vertical cabinet, traditional air handling unit, but you can buy lots of different types of systems, and you can also not do individual systems. You can also do central systems. So, on another building we're working on, it's a senior building. Nobody will be paying their utility bills. So there is no reason not to go with some sort of larger central system, often called, this is another heat pump system, often called a variable refrigerant flow or variable refrigerant volume, VRF, VRV type system, and serve multiple units off one exterior unit. This also gets to be really helpful if you have no balconies, right, where you can put it, and you have limited ground area for individual condensers, or limited roof area. If we're talking about net zero and we want to go load up our roof with solar panels, it's, we're starting to run out of room to locate that equipment. So, using centralized equipment has its place, and you're going to see that a lot more in New York, big urban centers where you've got a real premium on floor space and roof space. We certainly have seen roofs where they lift the solar panels up and they put equipment underneath them. There's a lot of advantages to that. There's also a cost to that. So that's not necessarily everybody's first choice. So I'm going to jump to ventilation. Does anybody have a particular mechanical system question they'd like to ask, or a burning item they'd like to bring up now while we're talking about mechanical systems?
Yeah, Emma, Steve Hall, can you hear me okay?
Yeah, I can. Yep.
Steve, you can jump in and ask it if you want, but he asked, with the individual unit system, are you exhausting to the exterior down the hallway?
In this case?
And Steve, you can unmute and just ask if you want to yourself.
Yeah, just, I'm just curious, and I think I missed the first part of your description of this, but if you're gonna have an ERV and I mean, I worked on a building recently where we were gonna just exhaust out, down the hallway to the exterior of the building and put the ERV there.
Yeah, so you're leading right into my next topic.
Oh,
So-
okay.
So let's go there. If anybody has any mechanical thoughts that jump to mind, we can go back. Yep. Dean, did you want to ask something else?
No, I was just going to, Jennifer has a question, but I think it's more general. So Jennifer, if you don't mind, we'll wait till the Q&A at the end, unless you want to jump in now.
No, very good. Thank you.
Okay, terrific.
So
All right.
on the ventilation side, and that's where Steve was going in this drawing here, I'm showing return air or exhaust air out of the bathroom. Here's my bathroom exhaust, and here's an exhaust out of the laundry closet going outside. And here's my fresh air supply into the living space and into the bedroom individually. So how is that happening? And you know, I talked a little bit already about how when we build really tight buildings, it's really critical to have a ventilation system. And in passive house buildings in particular, ERVs are essentially mandated, you know, because and an ERV or a energy recovery ventilator or a HRV, a heat recovery ventilator, are intended to offset the energy penalty of bringing in fresh air. So let me just talk a little bit more about, so those of us who have been designing for a long time, there is, we're required by code to exhaust bathrooms and kitchens, right? That's the spot ventilation piece. Then there's the sort of whole unit, whole building, whole house ventilation requirement, which when we build buildings tight enough, which we are doing, if we're doing this high performance buildings, we need to provide a certain amount of fresh air for both the space and for the people in the space. So there are, I have a whole spreadsheet dedicated to the different calculation methodologies to determine what that CFM volume of air is for a whole house. Passive House has its version, Energy Star has a version, LEED has 3 versions, depending on which version of LEED you're on. And then there's a code version, right? And we need to look at all of them and figure out which one rules, right? Basically, you end up with the biggest one takes over. And that's, you know, the simplest calculator is, you know, I think is the Energy Star, and I think it's in ASHRAE 62, 1 is, or 2 is the 7.5 CFM per person, bedrooms +1, plus a certain amount for your square footage. So that's what we're talking about here. And that's, you know, this is the kind of thing that most old buildings did not do well, right? A lot of the older buildings that we all live in don't have great ventilation. And that's, you know, it's not making a lot of us as comfortable. You know, now that we're all paying attention to ventilation, we're all thinking about how can we do this better and how can we retrofit some of our old buildings, especially places like senior centers and, you know, senior living, where, you know, we know that this has been really particularly critical. And not only that, but once we start introducing fresh air, the fresh air comes in cold, hot, humid, however it's going to come in, and you can't just dump it on somebody's head or else it's not going to be comfortable. So how do we do that effectively? So, you know, here are some choices of individual smaller type ERVs or HRVs. So on the left is Zender, which is sort of the high-end, high efficiency, high cost option that's available out there. There are differences in efficiencies across the ventilators, the energy, the ERVs and HRVs. And this, you know, so essentially what they do, right, is they take your exhaust air out of your building, which is 68, 70, 72, 75 degrees, whatever it is, depending on season and your set points. And they exchange heat so an HRV just does heat, and an ERV also does moisture. So it does allow for moisture to transfer from one airstream to the other. So you exhaust your conditioned air, you bring in your unconditioned air, and in the magic core in the middle, which is, there are different technologies for that. Sort of the easiest one to picture, I think, is if you think about foam core board, which has those little like holes in it. You've got air going through one set and then another one with the outside air going the other side, and the barrier between them allows the transfer of heat or moisture, but does not allow the transfer of smells, viruses, particulate, and things like that. So it allows for the transfer of energy and heat between those two airstreams, which offsets. So your incoming air, which may have been 10 degrees and hits a nice 70-degree airstream, can be 50 degrees or whatever it is. And that temperature is dependent on the efficiency of that magic core in the middle. How effective is it as transferring heat? So the Zenders are like the 90% efficient. They do a lot for you. And in general, all ERVs are more efficient in heating than they are in cooling. Partly just the delta T, right? You got 70 degree to 10. It's a lot more delta to get in the middle than with cooling, where you've got maybe 75 and 90. So, so there are choices for every price point. The Panasonic is probably the most cost-effective, best known. We all use a lot of Panasonic exhaust fans already. They have good controls. They're quiet. I actually have one running in the background in my room right now. So, these are good choices. They do, some of the things we've learned about ERVs. If you do individual ERVs, you add a fairly significant maintenance component to your operations, because you now need to change. Typically, they have filters of some sort in them, and they need to be changed and they need to be maintained. So you've added a whole nother piece of equipment in each unit that needs to be addressed. In terms of putting holes in your envelope, right? Every one of these requires 2 holes. There are concentric vent kits available for some of them. So that turns into 1 hole with sort of an exhaust powered out the middle and then intake around it. Or there's just, you can see all of these have 4 ducts out, right? You've got, an air intake and an air exhaust through the envelope. And if you're talking passive house and you're trying to minimize the number of penetrations that you have to seal so that when Nicole does her blower door, they aren't leaking, you want to, this may not be the most ideal choice, is to do it individual unit by individual unit. So that leads us to the design that we were using in that initial plan I showed, which is a semi-decentralized type system. So that was Steve who said yes to the hallway. So we've got exhaust from each apartment coming in, joining a duct that gets bigger to a centrally located ERV, exhausts out, nice fresh air intake, and then back to each unit along the corridor ceiling. So we're holding these, running them in our corridor ceilings, adding more stuff to coordinate in our corridor ceilings, and requires balancing, right? Because we want, this one, whatever, we've got a 2-bedroom, 2-bath here and a 2-bedroom, 2-bath here. They both need the same amount of CFM, but they're at different points in the duct run. Static pressure is what it is. So we need some sort of regulating damper, car damper, constant air regulator, or balancing dampers of some sort on these to ensure that we are exhausting what we required and providing fresh air as required. That gets, those rates are determined, and we need to be able to provide them and do them. So you will need to do some test and balance procedure with these units to ensure that they are hitting the mark. So they add some complexity, right? But we're at 2 penetrations instead of 20, right? So that's a whole lot easier in a lot of ways. It's also 1 unit to maintain instead of 20 or 10. in this particular case. So this is an option. And one of the reasons that we frequently see a horizontal sort of neighborhood design like this is to eliminate the need to combat stack effect, right? Older buildings, almost all the ventilation was done vertically. So if you picture these older buildings, they've got a fan on the roof, you're exhausting a stack of kitchens or a stack of bathrooms. Anybody who's done any work in those buildings know very hard to get them balanced properly. You know, the top unit, you'll pull a lot more air than the bottom unit. I mean, you can use the same sort of constant air regulators and it can be done. It's not insurmountable, but it's challenging to get it done. And, you know, because of the stack effect, it does sort of make that harder. And you hide all your duct runs in shafts, which is not as easy to handle later if you need to rebalance or adjust as putting them in a corridor ceiling. So this was the idea we started with on that last building, the one where I showed you the unit, which Steve called out, where's your ventilation going to? We started looking at it like this. And then in the end, we ended up doing 2 floors together. So this is a schematic, or it's actually a section from our Revit model showing this unit sitting in the mechanical room on one floor, distributing fresh air and exhausting to that level, and also running down to the floor below and doing the same thing on the floor below to the same set of units. You know, it's 2 floors that are, you know, identical up and above and below. And one of the reasons we did this was actually to get into a slightly larger piece of equipment that allowed us to do a full conditioning of the air that we're providing. So remember, we were talking about the ERV tempers the air that's coming in, but 50-degree air in the middle of winter dropping on the back of your neck, you know, not so bad. You can locate those close to your return on your heating and cooling unit, and it could pull it in, and, you know, you don't put it behind the sofa, and it could be good. It could be fine. This particular project wanted to put the ERVs on the emergency generator and use it to provide sort of a low level heating and cooling all the time. And it has a number of benefits. One, if you have an emergency outage, you're not going to cool down or heat up as fast, which is also inherently the case with a high performance building, right? The envelope's going to protect you for longer during an emergency power condition. And it allowed us to do this full conditioning of the air, which that full conditioning provides some constant dehumidification, which addresses some of those humidity concerns that I mentioned earlier. All right, I'm going to jump over into domestic hot water. I'm just trying to look at the time, make sure I have enough
And
time.
Emma, we do have a couple of quick questions on the ventilation side.
Yeah.
The first one is from Alicia, have you looked into the Minotaur, because it also handles HVAC ventilations and dehumidifies? And if you want to expand on that, Alicia, you can jump in, and then I'll go to Steve's after you talk about that.
Alicia, have you installed one of them? I am familiar with the Minotaur. Have you installed one?
Well, we have actually, yes, we have one in a passive house, zero energy, our own home. So that's,
cool.
You know, direct experience, and which includes an apartment. So it's kind of an interesting use case.
Okay.
And we're also familiar with a project right now in Boston where it is a multifamily building where they are being installed. So that's, but before I mention that, what I want to say is, as someone who's experienced sort of this, I've always hated air conditioning. I hate it. In fact, I'm sitting in a very freezy, chilly, air-conditioned space right now in Florida, which I was sort of chuckling when you said Pennsylvania, starting to feel a lot more like Florida, as is Connecticut. But, you know, what I've come to understand through high performance buildings is the reason I've always hated air conditioning is because it doesn't deal with the humidity in the air. And so now that I've been living in a dwelling that uses this Minotaur unit, I no longer hate hate air conditioning. And it's exactly what you talked about in terms of comfort. It's because it's handling, it's dehumidifying the air constantly, and it keeps it at this set point. And it's delightful. I've never experienced anything like this. It's probably more than you wanted to know, but I think it is
well,
important to kind of have like a personal experience. So anyway, go for it.
Yeah, I mean, the Minotaur unit inherently for everybody else is like we used to call it the black box, right? It does heating, cooling, and ventilation all in one box, right? So I talked about separating them, which is often the case that we use, but this allows it to be integrated into one box. And the Minotaur unit is, there are some more of these available in Europe. Minotaur is the first one. I think it's produced out of Canada, the guys from Montreal. And I haven't had the chance to install them yet. We have been looking at them for some projects. The project that most of the projects I've worked on so far have been bigger projects, and they haven't been willing to test them yet on that kind of scale. But I think that is potentially the way of the future, right? Is like a single unit that can handle all of this. And I don't know, Alicia, if you tested your house. One of the items that I've had people be concerned about with the Minotaur is how, because it's directly connected to the outside with all of that, is there, how does that test? How do you test it? And do you have any other sort of cross leakage going on?
I would say no cross leakage that we know of, but right. I did want to also point out, because I think someone else, I think maybe I saw a question in the chat about like the various other filters that can be part of a system. And the one thing that, again, I'm only speaking now from the Minotaur standpoint, but it has multiple filters, and one of them is sort of for particulate matter, but one of them is a MERV 8, MERV 15. There's a MERV 8 and a MERV 15 as well, and so that's also an additional benefit. And the other thing that you hit on, and again, you're hitting on some points that are so critical here, is the maintenance that comes with these systems. And I will tell you again, as a user or occupant, one of the things that I appreciate, and I hope that other systems incorporate this, is a reminder that tells you when to change your filter. And the Minotaur does, and I have to be honest, if it didn't have that, I'm pretty positive, as someone who is actually knowledgeable about the need to do this, I probably wouldn't do it. And that gets at the heart of these like occupant behavior, right? Like, how do we build these systems so they're smarter than the people living in them? Because I would totally lose track of that.
I mean, I'm so with you there. I should know better. And I'm like, every time I talk about this, I'm like, oh my God, when I'm done this presentation, I have to go check the filter in my furnace. Like, I have to go do that. But, and the other thing is like our cars, which are much less money than the houses and apartments we live in, have oil filter like, why do we not have those things on our houses? It's a huge asset. And, anyway. Was there another question that's relevant, Dean, that I should take now?
Yeah, Steve had a couple. One, any opinion on Ventacity ERV, VENTACITY?
Yes.
And then about the filters, HEPA or BPI to kill viruses. Both of those are. And Steve, feel free to jump in too.
Hope you did
it. So this larger unit that we ended up using is actually a Swigon unit. Ventacity and Swigon have much larger volume units, so they're appropriate for these sort of neighborhood ventilation opportunities. And they also come with the option to add a heat pump on the end of it to provide that conditioning. So yeah, I like the Ventacity units a lot. I like the Swigon units a lot. They're all higher performance. They're a little bit higher cost, Swigon in particular, but they meet the Passive House requirements. Passive House has very stringent requirements on ERV performance. So both of those are Swigon for sure. I think Ventacity also meets the requirements, and they're good. And Ventacity is from the Northwest, which I'm from the Northwest too. So I like that too. In terms of filtration, two things to think about filtration. One, yes, in terms of viruses and ERVs and ventilation. So bringing in outside air, we need to be intentional about where we place our louvers. So where we're bringing our outside air from. So in a multifamily building, you don't want to be locating your air intake louver next to your garage, right? Or next to the piece that's next to the highway, right? So we need to be intentional about those locations. On the other hand, we need to filter them at least for particulates, but we should be bringing in air that doesn't have viruses or anything like that in it. So there's a whole lot of talk about the kind of filters that will filter out viruses. That air is clean, relatively speaking, presuming that we bring it from somewhere decent, and we're more concerned about particulate in it. The air that we're recirculating, right? That's more critical to think about filtering for viruses, because that's the viruses are in our interior environment. All of these units are designed such that the airstreams are, the amount of contamination between the airstreams is less than 0.5%, right? So it's not allowing the transfer of viruses between the airstreams. The indoor air should be good, but in our heating and cooling systems that are recirculating, we want to be clear about that. And especially in our common spaces in a multifamily building, right? Because in our apartment, you know, we're at least, and we're, you know, I'm going to talk in a minute about compartmentalizing. We're just living with ourselves. So, you know, we need to be able to take our own precautions for that. But you know, and there are some minimal requirements for filtration under most of these programs to make sure that we're doing a decent job. But it's the recirculated air that we really want to talk about heavier filtration on. All right, so let me jump into water heating, and we'll just keep going. So one of the big challenges, if you are a believer in all electric and not conceding gas, which, and I will say the place where conceding gas frequently happens is here, because there haven't, until the heat pump water heater came along, the only real option for water heating was, you know, the standard tank electric, which is the most expensive way to generate generate hot water. And there are some really high performance gas hot water generators that are, you know, are very appealing and cost effective in terms of operational cost. So however, the heat pump water heater is here and has hit the mainstream. This is sort of this is a Ream one, which I think is the sort of, you know, the bread and butter of the industry, but everybody's got one now. And which means that, like, you know, like those inverter driven heat pumps that, you know, a few years ago, everybody was like, oh, are they really going to be good enough? And now we're all like, they're there. This is where we are with the heat pump water heater. And so the heat pump water, it's a heat pump, right? This piece on top is a heat pump. You can see the little air circulation requirements there's one on the other side. You take air in, you circulate air around this compressor. And it's just like your refrigerator or your air conditioner, right? You take, well, it's the reverse of your air conditioner and your refrigerator. So you're taking you're using the magic of refrigerant to take heat out of the air and transfer it to the water. And these water heaters have a COP usually of greater than 3, which means that, you know, a traditional electric water heater, you know, how many kilowatt hours or how many kilowatts it takes is a COP of 1, right? With these, a COP of 3. So you put in a third of the electric to get out the same value. So much better from an energy perspective, because we're talking about net zero, right? How can we get our usage down? So here's like a really great opportunity. So we've done a lot of these one-to-one. These units require air circulation around them. So one of the big issues initially was, how do you put it in a closet? Because you need air around it. You can't just stick it in a closet and close the door and hope for the best. It's going to subcool in that space. You need ventilation around it. So you need to duct it out or duct it in, or put it in a larger space. I see a lot of retrofits in existing homes, you know, in sort of single family homes, We have a colleague who went and put it in his damp basement. It has the side effect of cooling and dehumidifying because it's pumping out the cold air, right? So his formerly damp basement is now nice and dry. It's cold, but it's dry. So what we're doing a lot in multifamily is putting these on a corridor closet. So this, the air can be pulled out of the hallway and pumped back into the hallway. And that means, you know, generally hallways are cooling dominated spaces, right? We've got lighting in there. Sometimes we've got windows. So it's not a bad thing to have that there. We need to be cognizant of sizing our heating systems for the winter, so we're not subcooling those hallways as well, but usually the volume is sufficient. And we're either doing them sort of 1-to-1, one unit, one water heater per unit, or in this case, we did one water heater for 2 units. So these are 2 little 1-bedroom apartments, 1 unit. And this particular layout has been designed so you have really super short runs, right? One of the code requirements now that has become much more stringent is not allowing for long runs from your water heater to your tap, so that you don't waste water waiting for hot water and waste hot water waiting for hot water. So this kind of design is really critical to minimizing that wait time, which is wasteful. The other thing we've done with this is to put a gang of these units in a room, put in a heat pump to provide some more heating into that space, and gang them all together and do sort of a central or semi-decentralized heating system. So this was a small apartment building, 36 units on 6 water heaters. Once you start to add units together, your diversity factor gets better, right? So before we had 2 units on 1 water heater, here we've got 6 units. We've got more than 12 units on these, because not everybody is going to be using hot water all at the same time. And once, if you've got 2 apartments and both of them are showering, you need to have enough for that. But once you get into more than that, you can assume that your diversity is better, so you can downsize a little bit. So this is a nice opportunity to sort of use technology, which everybody's becoming fairly comfortable with. There are products on the market now which are not this sort of like a bunch of little ones ganged together, but larger, designed to be central, either using CO2 or various other exterior heat pumps. There's a Sandon, there's a bunch of them out there that are like not quite mainstream yet, but they're getting there. There are a number of places that are using them and a number of engineers who are using them fairly comfortably. The piece to consider with passive house in particular is that these pumps here, oops, I keep clicking. Not only do the pumps use energy, which is a fairly small amount of energy, what they do is they circulate the hot water through that loop all the time. That sort of length of run to your fixture requirement is also the length of run from the loop that you're circulating your hot water in, right? So this loop has to get within approximately, 50 feet or less of every fixture in the building. So you got a lot of piping all the way through the building to achieve this. And no matter how well you insulate that, it's still losing heat because it's still 120 degrees and your outside temperature is, your building temperature is 68 or 70 or 75 or whatever it is. So when you start to like reduce all of your other loads in passive house and high performance buildings, the domestic hot water starts to be your real driver of your energy usage, because we don't use less water. I mean, a little bit less because we put in low flow fixtures and all those kinds of things, but we're still showering, right? And we're still cooking, and that's not affected by the great envelope we put in. So this becomes a big driver. And once you do a distribution loop, somewhere between 20 and 30% of your spend for domestic hot water in a central system with a distribution loop is in losses in the distribution loop. So it's not attractive in a passive house situation, unless everything else is really in your favor and you're willing to do that, or you don't have space for these in every room. I mean, there are reasons why you would do it, and it's not inherently terrible. It's just something to be considered. All right, so Last item here, just to touch on that humidity piece. And so, you know, Minotaur apparently is working well for that. And I'm really glad to hear that. I'm looking forward to being able to try one of those somewhere. Our solution with this sort of constant run ERV that does some low level dehumidification is, I think, going to be very effective in the building that we designed that for. But what we're seeing in a number of cases is roughing in a location for a dehumidifier and then monitoring, right? So putting sensors in apartments and monitoring, because a lot of the need for the determination of whether you need a dehumidifier is going to be driven by the occupants of the space, right? If I live there with my 2 teenage daughters who shower all the time, and, you know, we all like to bake cookies, you know, we're going to generate a lot more moisture than, you know, if I'm living there on my own, retired, and I hate to cook and I order out all the time, and I get my hair done at the hair salon all the time, and I never shower, whatever. So your behavior as an occupant makes a huge difference to this. And so there will be cases where whatever we're doing is maybe not enough. And so as a plan for durability, we're seeing a lot of owners rough in a drain location and a plug location. So you can either put in freestanding or building in a wall mounted unit to address those cases where you're having additional issues with moisture. All right, I'm going to go through these last pieces. I think a lot of you are architects and have done work in Energy Star more than I have, or at least as much as we have. And so, as a big picture in terms of envelope, back to our 3Es, we talked a lot about equipment because that's my forte, and talking about envelope, we want to make sure, best practice is to install a exterior insulation, which is this here. Ensure we're addressing bulk moisture with some sort of rain screen on the outside, and ensure that we're being very intentional about where our air and vapor barriers are in our assembly, so we don't inadvertently create condensation in a place where we don't want it to be, which is the advantage of the WUFI models. They help us with that. When we input our wall assemblies, they can tell us more about where we might have issues. And the other real big issue is air sealing, right? So we've got the big issues with, bulk moisture, thermal boundaries, the benefit of the exterior insulation, right? To make sure we've got a continuous insulation barrier, not just in between studs, which is not as effective as the continuous boundary of insulation. And the other thing is, is infiltration, right? We're building tight. We're doing balanced ventilation with energy recovery. So we're not negatively pressurizing or positively pressurizing our units. So we should be minimizing our infiltration. But in order to really get there, we need to be very, very cognizant of our air sealing details and make sure that we're really addressing those. And the other piece of that is not just the exterior walls, which is our sort of energy benefit, but also compartmentalizing our unit. So if you see this, this is a tall building, this is the unit within that building. We want to make sure we're addressing air sealing on the party walls and on the hallway walls as well, because not so much for energy, more for odors, viruses, sound, pest management. I mean, there's a lot of really good reasons to do this well, which have nothing to do with, the energy benefits that I'm here to talk about. And, buildings that do this well, we have data that say they retain tenants longer, right? Because they don't have to deal with all of these, smelling the cooking from next door that they may not like, or, or all sorts of things. So big deal. There you go. There's my list. All right. So essentially the principles behind this is, the pencil rule, right? You want to be able to draw your air, vapor, thermal boundary around your unit and make sure that you're hitting it everywhere. And what really becomes, it's fairly straightforward in a lot of these places. The issue comes with, right, penetrations and junctions and joints. And you can see some of the pictures here, right? This is a dryer vent or a exhaust fan vent up here, and you can see the sealing that's being done to address that. Underneath stairs, if you've got sort of knee walls and places that are hidden. And the other big one is at sill plates, right? Sill plates and making sure that that sealing is happening. I'm sure Nicole and some others can give us even more stories about that. And again, talking about these trickier areas, the junctions of more than one wall, and making sure that we're addressing exactly where we're intending all of those boundaries to be. All right, I want to make sure that I don't run over here. So the last thing is to talk about engagement. And we've been sort of talking about this all along, but the Internet of Things is here, right? So there are solutions available to monitor spaces, to be aware of what's going into our apartments, and giving our tenants tools to also, have apps on their phone to control things, and so that we can, be best equipped to deal with issues. All right, so quickly going through here on the value proposition here, the intention here is that we will, and the overall driving philosophy behind Passive House in general is to drive our load so low that it's insignificant, the cost of our heating and cooling, right? Which is where, the hot water starts to dominate. But we want to drive down our utility spend significantly, which allows us more cash to deal with all of the other things that we need to spend it on. And also, doing all these things addresses risk, right? We're addressing durability, we're addressing moisture issues, we're addressing ventilation early, and in this whole design process, this sort of integrated design process, we're addressing those things early and documenting them well, which overall, it gets you to a higher valued asset in your building. And this is just to touch on, this, I'm not sure I love this graph, particularly. There's some better data, I think, out there about how, what I touched on about that this doesn't inherently end up making your building cost a lot more money, right? There are savings that we achieve by putting in much smaller heating and cooling systems, and ends up, in the end, being a benefit. And I think it's actually the PHFA, the Pennsylvania Housing Finance Organization, has some really good data on, they mandated Passive House for and then compared costs on buildings that were Passive House and not Passive House, and discovered that there was not a significant difference between the two types. So wrapping up here, pursuing this kind of building, we think it sets ourselves apart, right? We as designers prefer to work on this kind of building because we think that's our niche market. And we think not only does it set ourselves apart as designers and developers and property owners and managers, we're leaders, right? We as responsible, there's a whole mission driven side to this, right? We are helping to manage, resource management in the use of buildings. We all know how much energy buildings use as part of our total energy spend. And there are advantages. There are additional loan opportunities, density bonuses, tax credits available out there that can really be helpful with this. So I think that's it for me. Pretty pictures somebody put together. Anybody have questions?
Yeah, there are a couple. I want to let everybody
Okay.
know we've sort of reached the time bell time, but if people can stay on a little bit. Emma, can you stay on for a few minutes?
Yeah,
and
I
take
got a
some
few
questions?
minutes. I did not gauge my time as well as I should have. I'm usually better.
No, we
Apologies.
started a little late anyway.
Yeah.
So there's a couple in here from, let me see this one. First from Mike Ewell. Have you worked with any SAHP solar assisted products that are still heat pumps, but without the interior fan requirements? And then how often are your multifamily installations participating in demand response programs with the heat pump water heater? So they're both pretty technical questions. And Mike, if you're still on, you can unmute and elaborate if you need to.
Yeah, can you elaborate on that first question? The solar question?
Sure. There's a couple of products that are quote unquote solar assisted, which essentially means that the evaporator for the system is outside. So it's really the cooling is driven by wind and sun from the refrigerant, as opposed to running a fan on the unit itself. And therefore it leads it to just having one moving part of a pump to get the heat into the water. But then it removes that concern about moving air around the hot water heater inside of a building. And there's been a number of net zero energy installs like that in New York and Massachusetts. I just wasn't sure if you've worked with them and what your experience was.
Yeah, so I am familiar with what you're talking about. I have not, unfortunately, had the opportunity to do any of that yet. And I know I have had the opportunity to do some work with some people in the Northwest where they're putting some of these larger systems in sort of garages and things because the weather's a little bit milder there, and being able to put it all outside and have it connected to an inside unit. A lot of the larger systems are more like that. So I have not. I think that it's, it has a lot of advantages, right? Because you don't have to deal with that air balance and generating that cooling inside. On the other hand, sometimes the cooling can be helpful. So no, I haven't had a chance to do those yet, but I would say that it speaks to the fact that the technology is continually developing and we're getting much better. I mean, if people who learned about heat pumps in the 60s when they first came out, those the heat pumps we have now are, head and shoulders beyond those. And there's more and better coming every day. I just was at a Daikin launch for their latest product line, which does all sorts of other new things now, including inherent, like being all of their units being set up to being connected to the internet, so we can monitor them and adjust them and make ongoing algorithmic changes to improve the performance. So,
and Mike, do you want to ask your other question?
The question is about kind of
demand response.
Yeah, whether people have been selecting units with that consideration in mind, or whether anyone has had the experience of actually using it in that capacity.
Yeah, I haven't had anybody do that, but as I was just saying, like I was in on a information about some of the newer heat pump technology that's coming out. And one of the reasons to connect them to the internet is so that you can shed load and respond in a demand response way, so that you can, take advantage of that, either shed load so that we aren't overloading our electric grid at times when it's peak, and also take advantage of the pricing that comes with that, being able to do that. So I haven't had the ability to do that yet. One of the things that the developers of these products are also looking at is also driving down that MCA, that connected amp load. It comes up a lot in our retrofit work, where we're trying to do all electrification on a building that wasn't designed that way. And so we don't have enough electric in the building. So the vendors are familiar with this. And so they're like trying to drop that, sort of full load draw on these, so that we are, addressing the issues that we have in both retrofit and with, demand pricing.
Terrific. Okay. I noticed some people are having to jump for other meetings. So we have one final one from Jennifer. And I think this can open up to anybody who's on. I think it's a general question, but we have a client that has an old public housing building that has humidity issues. What do you recommend? I mean, it's a broad question, but
Yeah.
you can start, and anybody else can jump in if they've got ideas for Jennifer.
Yeah, I just was out at a diagnostic for a similar issue. It was a retrofit of a building in Philly. It's an old brick building and they left all the brick exposed so it would be pretty. And so there are two things that I look at immediately with those kind of things is one, what's going on with the envelope, right? Are we having air leakage or either bulk moisture or air leakage? So the air leakage will take moisture with it, right? And are there bulk moisture issues? So in this particular one, there was a sill above the windows that wasn't properly sealed. So they were getting bulk moisture in on top of it. The brick was not sealed very well on either side either, and they didn't insulate. So there was moisture coming straight through that. So look at your envelope. And the other one is look at your ventilation, because this building was significantly negatively pressurized. So it's exacerbating that issue of bringing in moisture from the outside. If you've got exhaust running continually, and a lot of older buildings do have exhaust only systems that are running up the building, a shaft of exhaust, which may well not be exhausting exactly how it was intended. It may have, a lot of these older shafts, as they've done renovations, they've hacked holes in them and who knows what they're connected to now. So you may be looking at moisture and air coming in through all sorts of pathways that you don't even know about. So I would look at the ventilation and look at the envelope. Those are the things that I usually start with moisture issues.
Okay, terrific. All right, everybody. Well, Emma, it was great. Great presentation.
Excellent. Thank
Generated
you.
a lot of questions and all that other stuff. All right. Well, with that, many thanks, Emma. Thanks, everybody, for coming.
My pleasure.
Quick update. We're not going to have a meeting next month due to the holidays, but we'll pick up again in January. And we've been busily identifying topics and people to talk. So stay tuned for more. And in the interim, have great holidays and enjoy the weekend coming up now. All right. Thanks, everybody. Have a good ones.
Thanks, everyone.